Good day, I'm J Wildberger. Now we have some slightly longer videos that we can play with, so it's probably a good time for us to stop and have a breather and review some of the material that we've already been talking about in this series. This is a series on the foundations of mathematics, where I want to do several things. I want to first of all propose a logical, relatively clear, relatively simple approach to building up mathematics from the start. And I want to cover most of the main areas of mathematics systematically and consistently, so that we have a strong logical position throughout the subject. One of the other aims is to strengthen mathematics education. I believe that having a proper framework for the subject in terms of the theory will make it much easier for mathematics educators to try to figure out what they should be teaching students at various stages. So although we're not directly feeding into school curriculum, indirectly laying the foundations ought to have a major impact to mathematics education and structuring curriculum for students. Now, to be honest, there's a third aim of this series, which is to bring down modern pure mathematics a few pegs. I'm firmly of the opinion that modern mathematics has gone astray, that logically it no longer hangs together properly. And I know that my fellow colleagues are going to be reluctant to admit that, but I'm going to try to expose the flaws and the weaknesses of the subject so that we can move ahead, so that we can fix them and move towards a brighter, more consistent, more pleasant approach to this greatest of all subjects. Okay, so in the last few videos we've been talking about our approach to polynomials, and we've approached it through an idea called a polynumber. So it's probably a good idea for us to have a review of the basic structure of arithmetic that we've developed so far. Let's go right back to the beginning of the series, where we started out by talking about arithmetic with natural numbers, and then integers, and then fractions, and then finally rational numbers. So we did that in stages. And it's instructive when we start thinking about arithmetic with polynomials to go back to arithmetic with ordinary numbers. Because as we'll see, the two subjects are very parallel, have a lot of close connections. Alright, so from our very first video in this series, you may remember a long time ago, we introduced natural numbers in a very naive way, just as a bunch of strokes on a line on the page. And at first we just had very naive kind of names for these things, but eventually we talked about the Hindu Arabic number system, and that's the one that we're now going to be using subsequently. So we have our idea of natural numbers, we have operations of addition and multiplication defined on natural numbers. The next important step is to define what an integer is. So we defined what an integer was in terms of what a natural number was. And let me remind you that what we did is we chose ordered pairs of natural numbers to be integers. So the ordered pairs, say m and n, we like to write in this notation. So m and then sort of a downward slash n. And we're thinking of this as sort of being a little bit like subtraction. Okay, and we say that this is m less n. And m and n are natural numbers. These are the things we've defined at the first stage. And there's a crucial notion of equality, that m less n equals k less l, precisely when m plus l equals k plus n. So these objects then become the integers. So for example, 7 less 4 is what we would normally call 3. And 4 less 7 is what we would normally call minus 3. This one here is rather special. 1 less 1, that's the number 0. And when we move from the natural numbers to the integers, we enlarge our arithmetic because we can now talk about subtraction along with addition and multiplication. Now there's another possible way of extending the natural numbers, and that's by introducing essentially, well, fractions. Okay, so fractions is a new type of mathematical object which are also ordered pairs of natural numbers, just as integers were. But now the notation is slightly different. We have an m with a sort of upward slash n. And our agreement is that m slash n, or m over n as we prefer to say, equals k over L, precisely when m times L equals k times n. So these are the things that we usually call fractions, or sometimes positive fractions, but we'll just say fractions. So things like 1/2 and 1/3, and we can define the operations of addition, multiplication, and division for these fractions. So for example, 1/2 plus 1/3 is 5/6. And note the pretty close similarity between these two concepts. The only difference between the equalities here are replacing the plus operation with the multiplication operation. Alright, so we've started with the natural numbers as a type of mathematical object. We've created the integers as a new type of mathematical object, and also the fractions. And now the culminating thing is to sort of to combine those two ideas to get the rational numbers. And what we did is we got the rational numbers this way by going from the integers and doing something to integers. And what we do to the integers is really the same kind of thing as we did from numbers to get fractions. We consider ordered pairs of integers now, so a and b are integers, and we consider expressions of the form a over b, where a and b are integers, but a special requirement that the second one, b, must not be 0. And the notion of equality between these rational numbers was very much like the one up here. A over b equals c over d, precisely when AD equals BC. Okay, and now the rational numbers, which intuitively are just all the fractions where we include negative fractions as well as positive fractions. All of those form what mathematicians call a field, meaning we have 4 operations: plus, times, those are our original 2, and then 2 new ones, in some sense the inverses of plus and times, minus and divide. And we have various laws that these operations satisfy, and we get a very beautiful closed domain for doing arithmetic. This is the field of rational numbers, and this is where most of mathematics ultimately takes place. Very strong statement. All right, most of mathematics ultimately takes place in this field of rational numbers, or something that's pretty close to it. It's a very, very fundamental object. So that was arithmetic. In some sense, that's sort of primary school arithmetic. Now we move to high school arithmetic, where we go up a level and look at more sophisticated analogs of each one of these 4 types of objects. All right, so from the primary school to the high school is going from numbers to polynumbers. So we started studying positive polynumbers. These were a type of mathematical object that we gave this name for, polynumber with a plus sign. And the plus sign refers to the fact that we're including 0 as well as the natural numbers. So we're going a little bit past the natural numbers, including 0 in the coefficients allowed. So a positive polynumber is just a column of natural numbers or 0, a finite column, with a little bracket up on top. That little bracket tells us, alerts us that we're talking about a polynumber. Okay, I'm not going to review everything, but just a brief idea. We have a polynumber P and another polynumber Q. They don't have to have the same degree. We can add them. We do that in the most simple way. We add each level. 2 plus 1 is 3, 0 plus 4 is 4, 13 plus, well, there's nothing here, so it counts like 0, is 13. Multiplication is more subtle. So at the top level, sort of the 0th level, the multiplication of these two is just like ordinary multiplication. 2 times 1 is 2. At the second level, what we do is we take this times this plus this times this. So 2 times 4 plus 0 times 1 is 8. At the next level here, we take this times whatever is here, plus this times whatever is there, plus this times whatever is there. Well, the only one that's non-zero is 13. And at the next level, 2 times whatever is here, 0 times whatever is here, 13 times 4, 0 times 1. 13 times 4 is 52. Okay, and then we talked about the arithmetic of these positive polynumbers. And then we enlarged our view somewhat by introducing more general objects, by introducing polynumbers whose coefficients are allowed to be negative, as well as 0 or positive. And the addition and the multiplication of those polynumbers are just as before, except that now there's possibly negative numbers floating around too. And we also introduced some notation for converting a positive polynumber as a column like this to a more standard looking polynomial type object. And the way we did that is by introducing a symbol for a very special polynumber. The polynumber, which is sort of the smallest one, which is not actually sort of like a number. The ones up at the top here are acting just like ordinary numbers. The next one down, this one here, is the first one that's sort of beyond the numbers. We're calling it alpha. Then alpha squared is this one with 2 zeros. Alpha cubed is this one with 3 zeros, and so on. And with the help of these powers of alpha, we can write an arbitrary polynumber like this as 3 times alpha to the 0, by convention that's just like 1, plus minus 1 times alpha to the 1, plus 0 times alpha to the 2, and 1 times alpha cubed. And we eventually agreed that we would relax our notation. So this polynumber here has another name. This is the standard alpha form for this polynumber. It's just another way of writing down the same mathematical object. And now it turns out that this is, well, rather familiar to anybody who's done high school or college mathematics. It's a polynomial in alpha. And then it turns out that the addition and the multiplication and the subtraction of these polynomials are just exactly the same as the corresponding operations on the associated polynumbers. So whether we're working with polynumbers or with polynomials, it really comes down to the same thing. The advantage in this point of view is that we compress the definition of a polynomial to its essentials. The essential aspect of a polynomial is the row or the column of coefficients. The variable itself is actually rather unimportant. And here we've introduced the variable, a rather specific one, only sort of as a secondary step, just to allow us to write the polynumber in a different way, actually sort of more horizontally rather than vertically. That's what we've done so far. So I'd like to just back away one step now and have a look at sort of the general picture that we're developing. We've talked about the various objects in ordinary arithmetic with natural numbers, integers, fractions, and rational numbers. And what I'd like to do now is introduce the idea that the poly situation is in some sense a mirror of this one, just sort of up a level in complexity. So for each of the objects over here, there's a corresponding kind of object over here. So natural numbers correspond to something that we might call natural polynumbers. Integers correspond to something we might call integral polynumbers. Fractions to fractional polynumbers, and rational numbers to rational polynumbers. So what are these various things? Well, I'd like to proceed a little bit differently than previously, so this is a reevaluation of polynumbers now. By starting with this one right here. We haven't actually defined polynum as a type yet. We started by defining positive polynumbers, where zeros were allowed. Now we're going to say, well, actually, when we started with natural numbers, we didn't include 0. Right? 0 is actually a relatively sophisticated idea, going back to the Hindu Arabic system. It's more naive, it's more simple-minded to think of an arithmetic that doesn't have a 0. So what would happen if we started thinking about polynumbers in that framework? Now we only have 1, 2, 3, 4, 5, and so on. Well, that means we would be talking about polynumbers, columns of natural numbers now, with no zeros allowed. We could still include alpha as the polynumber 0, 1, just as before. So we could still rewrite this polynumber in, say, this horizontal or standard alpha form. And we would still have the operations of addition and multiplication. These are all natural numbers, these are all natural numbers, and you add them, you're still getting all natural numbers. Similarly, if you multiply two of them, you always get natural numbers. So this is a nice little closed system, which is smaller in some sense than the positive polynumbers we were considering before. So in trying to keep an analogy between these two things, it's now an interesting thing to contemplate these polynumbers as sort of fundamental building blocks for polynomial arithmetic, just the way natural numbers were the building blocks over here. So from that point of view, how would we then proceed to define integral polynumbers, fractional polynumbers, and rational polynumbers? The answer? Exactly the way we proceed to define integers, fractions, and rational numbers over here. We can mimic exactly what we're doing over here, and even better, the proofs that we need for the various laws that the operations satisfy over here, more or less work over here without any significant alteration. This is an economy of thought and an economy of work. And it's clearly a kind of a mirroring that we should respect. So let's just briefly have a look at how that would go. It's a slightly different way of thinking now about polynumbers. So how would we define integral polynumbers? Well, we do it just the way we define integers in basic arithmetic. An integral polynumber is just a pair of polynumbers, written in this expression, p less q, with exactly the same kind of convention that p less q equals r less s, precisely when p plus s equals r plus q. So for example, this polynumber less this polynumber would be the same as this one less this one, because this one plus this one would be 7, 7, 6, and this one plus this one would be 7, 7, 6. Now both of these, in our minds, represent the integral polynumber that we would previously have written like this. Because 4 less 6 is really minus 2 as an integer, 1 less 5 is really minus 4 as an integer, 6 minus 1 is really 5. It doesn't matter if we use these two or these two, we still get the same. But it allows us to define an integral polynumber not as a polynumber consisting of integers, but rather as a pair of polynumbers, natural polynumbers, if you like. Well, the operations are just as before. Effectively, nothing changed. Computationally, it doesn't change. It just means that we have a slightly different definition of what an integral polynumber is. Exactly in a parallel way, we can do the same thing for a fractional polynumber. I remind you that an ordinary fraction was a pair of numbers, a over b. So here, a fractional polynumber is a pair p over q, where p and q are natural polynumbers. This convention is a convention for equality between fractions. P over q equals r over s, precisely when p times s equals r times q. kind of the multiplicative analog of that one. So for example, here is a fractional polynumber now. 1/4 over 231. That's equal to 312 over 693 because, well, because this times this equals this times this. Or a simpler way of seeing it is just that if you take this one and you multiply by 3, you get that. You take this and you multiply by 3, you get that. Now, this is a strange kind of object until you perhaps rewrite it in standard alpha form. If you do that, then say this one here would be 3 plus 12 alpha over 6 plus 9 alpha plus 3 alpha squared. This kind of expression is something that we build up from polynumbers by allowing division. But the formal definition of what a fractional polynumber is it's a pair of regular natural polynumbers. And this is the way we can sort of write it down in a more familiar way. And these fractional polynumbers, well, their operations that they allow are addition, multiplication, and division. And all the numbers that are entering here have to be natural numbers, bigger than 0. So now we get to rational polynumbers. These are going to be very important objects for us. They are very important objects in mathematics. And our definition of them is entirely analogous now to the way we define rational numbers from natural numbers. First we start with natural numbers, then we go to integers, then we go to rational numbers. Here in the poly situation we start with natural polynumbers, go to integral polynumbers, then to rational polynumbers. So a rational polynumber is a pair, p over q, where p and q are now allowed to be integral polynumbers. In other words, they have negative signs possibly in their coefficients, and zeros as well. The convention for equality is exactly as the same for fractions and exactly the same for regular rational numbers. And here's an example of a rational polynumber, 1, 0, minus 2 over 2 minus 5. If we multiply both of them by 2, we get 2, 0, minus 4 over 4 minus 10. Those are the same rational polynumbers. And in standard alpha form, this one here, say, is 1 minus 2 alpha squared. This one is 2 minus 5 alpha. So we're talking about this object, which is usually called a rational function in mathematics. A rational function in the variable alpha. But there's no function actually involved here at all. Okay? It has nothing to do with functions at this stage. This is simply an expression that we create by taking the formal quotient of two integral polynumbers. Okay, now with these objects we can now do all kinds of arithmetic because we have 4 operations. And what is the definition of these operations? So we have to define addition, we have to define multiplication, subtraction, division. Well, these definitions are exactly the same as the definitions for those operations for rational numbers. I hope they look familiar, right? If you just looked at them, you wouldn't be able to tell that I'm talking about polynumbers. You might think I'm just talking about ordinary rational numbers. The laws are exactly the same. And the proofs of the formulas, the laws that these operations satisfy, they're also pretty well exactly the same as for rational numbers. That's the advantage in carrying everything over from ordinary numbers to polynumbers completely without losing anything, without dropping anything. Everything's just moved right over. So everything still basically works. Okay, it's still necessary for one to write these things down, okay, but I'm not going to do that. It's a great exercise, and eventually we're going to talk about a project that we can attempt to try to get people to actually start contributing to writing some of these important things down in a way that's accessible and usable by a wider community. Right now, I just want you to ingest the definition of a rational polynumber. This is going to play a big role for us as we move through Foundations of Mathematics, because it'll turn out that this gives us the second most important field in mathematics. So the field of rational polynumbers is the second most important field in mathematics, in my view, after the rational numbers. And in some ways, it's very parallel to it. Here is a little interesting aside that some of you might like to think about. In our square with 4 objects, we went from natural numbers to integers down to rational numbers. But the diagram suggested that you should also be able to go from natural numbers to fractions to rational numbers. In other words, we should be able to define rational numbers once we have fractions defined, but perhaps integers not defined. So I'm going to leave it as an exercise for you to how do you go from fractions to rational numbers. And the corresponding poly question would be how do you go from poly fractions to polyrational numbers. So we are going to talk a lot more about the arithmetic of rational polynumbers. This is just an initial orientation to how we are going to proceed. I want you to have firmly in mind this parallel between ordinary arithmetic and polyarithmetic. The difference between primary school arithmetic and high school arithmetic in a simple kind of way. Alright, so a good preliminary to actually doing arithmetic with rational polynumbers is to think a little bit about division with ordinary integral polynumbers. And that's what I want to talk about for the rest of the lecture today. We're going to just talk about how do you divide one integral polynumber by another. So let's have a look at this example here. In standard alpha form, here is one polynomial. Here's another polynomial. We're multiplying them together. And let's just check that we get this polynomial here. So how do we multiply when we have sort of them both in horizontal standard alpha form? Well, the first entry is 2 times 1. The next entry over here is 2 times 3 plus the coefficient here, 1 times 1. That's 7. And then the next entry, alpha squared. Well, it's 2 times the alpha squared term over here, but there is no alpha squared term there. Plus 1 times 3, which is 3, plus minus 1 times 1, for a total of 2. And the alpha cubed term, well, for that it really amounts to just asking, well, how can you get an alpha cubed? You can get an alpha cubed only by multiplying that alpha times that alpha squared, and the coefficient is minus 3. So over here is the corresponding multiplication in our usual original way of thinking about integral polynumbers. You can check it there. Okay, so this polynumber times this polynumber is this polynumber. So it follows that if we take this polynumber and divide it by this polynumber, we should get this one. In other words, the definition of division of polynumbers should be exactly this. That if this times this equals this, then this divided by this equals this. Or conversely, this divided by this one equals that one. So division is the inverse operation to multiplication. Okay, so now here's an interesting computational problem. Suppose that we didn't know what the answer was. Suppose that we knew that this was a factor of this one. We knew that there was some polynomial that multiplied this one to get this one. How would we get that polynomial? How would we figure out what this right-hand side is if we're just given these two polynomials here? Or the other way around, how would we get this thing here if we just knew the numerator here and the denominator? Well, if we think about it for a little while, suppose we're sort of thinking, what could the possibilities be for this polynomial over here? Well, it's got to have the property that when we multiply it by this one, we get this one. So the constant term here times the constant term here equals 2. That means that the constant term really has to be 1. And similarly over here, the constant term on this side, whatever it is, times 1 has to be 2. So in this case, the constant term has to be 2. All right, so that gives us an idea that maybe we can work systematically, sort of figure out what the first term is, and then what's the second term, and what's the third term, and work systematically. In fact, we can do exactly like that, and it's really just the process of division thought about in a slightly different way. It really goes back to the long division that we did for ordinary numbers. But in fact, it's a little bit simpler in a way. So let's have a look at this important algorithm of how to divide one polynomial by another. So we're going to set things up just the way we did for division of ordinary numbers. And you might like to go back to that earlier video in the series where I talk about division. So we want this polynomial divided by this polynomial. We'll write a line, another vertical separation there. And what we're really doing is we're asking how many copies of this polynomial can we fit inside this polynomial. It's the same kind of question as dividing 36 by 9. You want to know how many 9s fit inside 36. Now, the situation is made somewhat easier here in this situation because all the powers of alpha are clearly separated. We can start on the left. We can say, all right, that's our 2 there on the left. That's the order 0 term, or the constant term. Over here, there's a 2. So we have to multiply this thing once to get that 2. So we're going to take one copy of this thing initially. And there's the one copy right there. I've just copied it again. And we're going to subtract that one copy from the original polynomial. 2 minus 2 is 0. 7 alpha minus alpha is 6 alpha. 2 alpha squared minus alpha squared is 3 alpha squared. And minus 3 alpha cubed, well, we're not subtracting any alpha cubed, so we still have minus 3 alpha cubed. So we've taken away one of these polynomials, and now we have this somewhat smaller object. And we want to ask, well, how many of these fit inside here? And again, we look at the lowest term right here, which is 6 alpha. And here the lowest term is 2. And so we can, just disregarding everything else, just looking at that 6 alpha and looking at that 2, we say, all right, 3 alpha times this one will match up with that 6 alpha there. So we'll take 3 alpha copies of this. In other words, we'll multiply this by 3 alpha, giving us 6 alpha plus 3 alpha squared minus 3 alpha cubed. When we take the difference, we get exactly 0. So altogether, we've taken away how many copies of this? 1 plus 3 alpha copies of this. And so that's the answer. So I emphasize this is just like long division for numbers, except it's simpler. It's simpler because we don't have to worry about carries. Each of the powers of alpha acts completely independently of the other powers of alpha. When we're doing ordinary arithmetic with powers of 10, the powers of 10 can overlap. If we have more than 10 tens, or actually more than 9 tens, we have to create 100. So the tens contribute to the hundreds column. And that kind of carrying can become quite complicated. Here, nothing like that is happening. Every column stays just within itself. But you can see now why the long division process or algorithm for ordinary numbers is important. It's important because it's setting up this important algorithm for doing polynomial division. This is why students who have not learned long division are at a great handicap when it comes to doing algebra, because they cannot divide one polynomial by another. Their calculators, most of the time, will not do that for them, and they've never learned how to do it by hand. It's a big shame, okay? Division is very important. It's an important operation. It's important to understand how that goes. Let's have a look at this example from a different point of view. This is not the only way that we can arrive at this answer. So let's look at that same question, but in a slightly different way. So there's the polynomial that we want to divide. We want to divide it by this. Now what we're going to do is we're going to say, all right, let's think about starting not with the lowest order terms, but rather the highest order terms. The highest order term here is a minus 3 alpha cubed. So how many of these things will fit in here in order to get rid of that minus 3 alpha cubed? We want to sort of cancel it. Well, 3 alpha of them. If we take 3 alphas of these, then we'll have minus 3 alpha cubed. Then when we subtract, we'll get 0. So if we multiply this by 3 alpha, well, we also have 6 alpha plus 3 alpha squared and minus 3 alpha cubed. When we take that away, so this minus this, we get 2 plus alpha minus alpha squared, and of course 0 here because we arranged that. So we've taken 3 alphas of these away, and now we're left with this, and we ask how many of these fit into here. The answer is exactly 1. 1 times this is that, the difference is 0, and we get the same answer, of course, 1 plus 3 alpha. So the moral of the story is there's a bit of ambiguity, or there's some choice here. When we're dividing, we don't necessarily have to start on the left. We don't necessarily have to start on the right. We can choose which one we want to do. Okay, so if we know that the division works exactly, which we do in this case, in other words, we know that there's no remainder at the end, then both methods work. And both methods have something to recommend them. I like to think of the first method, which concentrates on the lower powers first, as a sort of an analytic approach. And to think of the second method, which works on the higher powers first, as a more of an algebraic approach. But that's just the way I think about it, but it might be useful for you to think about that too. So I suppose this is actually more in keeping with what actually happens in the Hindu-Arabic system. In the Hindu-Arabic system, it's the highest powers of 10 that you work on first. Right. These are actually sort of the highest powers of 10, even though we've written them here on the right-hand side. Did we really need to work in the standard alpha form? Could we have done this all with the polynumbers themselves, with the actual columns of numbers? Well, yes, we could have. Let's have a look at how that would go. Now we're working with columns, so we're going to orient our work a little bit differently. Instead of sort of going down, we're going to go across. But I hope you'll see that the idea is very similar. So here we have this polynumber divided by this polynumber. This is now the second case that we're examining. Okay, so the question is, how many of these fit inside here? Well, there's going to be 2 solutions. So there's solution number 1, and there's solution number 2. The solution number 1, we're going to concentrate on lower powers first, sort of the analytic approach. So we look at the top here, look at this 2, and say, okay, how many of these do we need to get rid of that 2, or to match that 2? The answer is exactly 2 of them. 2 times this will be the polynumber 2, 6. And now when we take this polynumber and subtract 2, 6, so we're going across now, subtracting. That bar means the result of the subtraction. 2 minus 2 is 0. 7 minus 6 is 1. 2 minus 0 is 2. Minus 3 minus 0 is minus 3. So we now have this one. Okay, now what polynumber do we have to multiply by in order to sort of get rid of the next non-zero term here, this 1. How many of these can we subtract from this one? The answer is 0, 1 of them. In other words, if we multiply this polynomial by 0, 1, remember the effect of that is simply to move it down 1. So we're getting exactly this polynumber here. And that's one that matches up with this one here. So when we take the difference, we get 2 zeros now, and also a -1 and a -3. So now we're at this stage here. We ask how many of these will fit into here. The answer is this many of them. We have to multiply by 0, 0, -1. The effect of which is to move this thing down 1, 2, and also multiplied by -1, giving us exactly that. We take the difference, we get 0. So altogether we've taken this polynumber, multiplied it by 2, by 0, 1, and by 0, 0, -1. In other words, by the total polynumber 2, 1, -1. That's the answer. That was the polynumber we were calling 2 plus alpha minus alpha squared. So you see, the powers of alpha are not needed at all. They're just a way of keeping track of what's going on. But the positions of things will do that for us as well. Here's the algebraic approach, the same question, the algebraic approach where we try to get rid of the higher order terms first. So we look at this polynumber, the highest order here is the -3. How many of these do we have to use to get rid of that -3? Well, we'll multiply this one first by 0, 0, 1, that'll sort of slide it down 2, and then by -1, that'll give us exactly this polynumber. I haven't put the 0 zeros there. When we take the difference, 2, 7, 3, 0. Now we're at this level here. How many of these fit into here? Multiply by this polynumber. Shift down 1, multiply by 1 to ensure that we're getting a 3 there. Then that 3 will cancel with the 3 that's there, and we'll have a 0 at the next level. So here we're working sort of up from the bottom. Here we were working down from the top. Okay, so after we've multiplied by this one and subtracted, we get 2, 6. And that's just 2 times this one here. And the difference is 0. And the total that we've subtracted is 2, 1, -1. So here's how you can practice this. It's a very good thing to practice. Take the product of two polynumbers. Just make up any two integral polynumbers and multiply them together. All right? And then you take the result and divide it by one of them. You should get the answer, which is the other one. All right? So if you put it aside for a day or two, you may have forgotten what the second factor was, and then you can divide the product by one of the factors, go through the algorithm, see if you can recover the original second factor. Okay, you can try it both ways. You could try it just using the numbers, the columns of numbers, the polynumbers themselves, or you can do it in the somewhat more familiar sort of long division form with things in alpha form. This discussion suggests that maybe it would be nice to have polynumbers which are, instead of being columns, which are rows. Then we could apply the same kind of algorithm as we did on the previous stage, but without any alphas. Just have polynumbers where we had the polynomials. So does it make sense to talk about row polynumbers? Well, yes, it does. And it's actually most interesting if we think in our minds of having both row polynumbers and column polynumbers sort of floating around at the same time. That adds an interesting two-dimensional aspect to things, which on the polynomial side is really amounting to having a polynomial in more than one variable. When we consider polynomials, we often want to work with more than one variable, and next time we're going to talk a little bit about that, introducing a two-dimensional aspect to the polynumbers that we're considering. So row polynumbers as well as column polynumbers next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.